All right, so you're here with us today, and I think it's safe to say you're probably pretty interested in how the whole chemical industry is changing, all the stuff about catalysts and reaction engineering and how we can actually start making chemicals in a way that's better for the planet, right?
Yeah.
And so today we're going to zoom in and focus on one specific reaction that kind of sums all of that up, and it's called the methanol-to-olefins process, MTO for short.
Yeah, exactly. And if you're listening to this, you're probably studying chemistry or material science, maybe even working in those fields. And I'm sure, just how essential those light olefins are, ethylene, propylene. Those are the C2 and C3 building blocks that go into making like so many different polymers, fibers, resins, everything really. I mean, they're super important in modern industry. And this MTO reaction is a really interesting way to make those olefins, and it's becoming more and more important all the time.
Totally. And we've been digging through all the latest research papers and going back over our own notes, trying to pull out the most important stuff that you need to know about this. And the whole point of this deep dive is to give you a good, solid understanding of this MTO reaction, where it came from, how important it's becoming in this whole methanol economy thing,
Yeah.
and the really big role that nanocatalysis plays in making it work better.
Yeah.
So we're going to go into some detail, but we're going to try to keep it clear and easy to understand.
Okay, so first let's go back in time a bit and see where this MTO process came from. I mean, it didn't just appear out of nowhere. The thing is, it became a really attractive alternative way to make olefins, especially in parts of the world where there's a lot of natural gas and coal, because those are the main things you need to make methanol.
Yeah.
So it was a way to kind of branch out from the traditional ways of making olefins that relied on crude oil.
And we should give a shout out to some of the big companies that really helped to make this happen on a large scale. Companies like Mobil, UOP, Sinopec. I mean, they put a ton of money and effort into the research and development to take the basic chemistry and turn it into actual MTO technologies that could be used in industry.
Yeah, and the reason they did that is because ethylene and propylene are so important in so many different industries that any new way of making them is going to be a big deal. Traditionally, most of these olefins have been made by steam cracking naphtha, which is a part of crude oil. So the MTO process offers a really valuable way to get these olefins from a different source, which makes the whole supply chain more resilient and opens up new economic possibilities.
And if you're interested in sustainable chemical production, which I'm guessing you are if you're listening to this, then the MTO process is really interesting because it's closely connected to this whole idea of the methanol economy. Methanol is becoming more and more important, not just as a solvent in a chemical, but as a potential fuel and a versatile starting material to make lots of other valuable chemicals, and MTO is a key part of that.
Exactly. It's all about finding ways to make the things we need without relying so much on fossil fuels. And the MTO process has the potential to help us do that by using carbon sources that don't come from petroleum. But of course, there are still some challenges. The research shows that we're still working on things like preventing the catalyst from deactivating too quickly, often because of those pesky aromatic byproducts and paraffins and coke that form. And of course, we're always trying to improve the selectivity of the process so we get more of those light olefins that we want. Those are still really active areas of research.
Okay, so we've got a pretty good idea of why this technology is important, where it came from. But now let's get into the nitty-gritty, the actual chemistry that makes this conversion of methanol to olefins happen.
So basically, the MTO process happens in two main stages. The first one is where the methanol gets activated and you start to form this complex mixture of hydrocarbon species that are stuck to the surface of the catalyst, and we call that the hydrocarbon pool, or HCP. In the beginning, two molecules of methanol lose a water molecule in a process called dehydration, and they form dimethyl ether, or DME, and the equation for that is 2CH3OH gives you CH3 OCH3 plus H2O.
So the DME is like an activated form of methanol. It's an intermediate that gets the whole process going.
Yeah, exactly. Once you have DME and some leftover methanol on the active sites of the catalyst, they start to react and form this diverse hydrocarbon pool. It's like a constantly changing collection of all sorts of organic molecules, including things like carbenium ions and cyclic hydrocarbons. And these are the real intermediates that eventually lead to the formation of the olefins that we want. And the exact makeup of this pool and the main mechanisms of the reactions that are happening there are still being studied very intensely.
A whole pool of hydrocarbons. It sounds kind of random. How does it go from that mess to making specific products like ethylene and propylene?
That's what's so cool about catalysis. The specific environment that the catalyst creates is like an orchestra conductor. It directs the whole series of transformations. And this brings us to the second step, the part where those light olefins are actually formed. It's a whole cascade of reactions, methylation, which means adding methyl groups cracking, which means breaking apart those longer carbon chains, and cyclization, which means forming ring structures. And all of these things are happening with the molecules in that hydrocarbon pool. They're interacting with the methanol, and eventually they produce what we're after, ethylene, propylene, and water as a byproduct. So the overall transformation looks like this. CH3OH gives you C2H4 plus C3H6 plus H2O.
But you mentioned those side reactions before. What are they exactly? And why are they a problem?
Yeah. Well, the problem is that the environment inside those catalyst pores is so reactive that it can also make some heavier products that we don't really want. Things like aromatic compounds, paraffins, which are saturated hydrocarbons, and coke, which is basically carbon deposits that gunk up the surface of the catalyst and block the active sites where the reactions need to happen. These side reactions make the catalyst deactivate over time, which means it becomes less efficient, and eventually we have to regenerate it or even replace it, which is expensive and time-consuming. So that's why it's so important to make the process as selective as possible, so we get mostly ethylene and propylene and not too much of that other stuff.
So this is where nanocatalysis comes in. It seems like designing and optimizing the catalyst at the nanoscale is the key to making all this complex chemistry happen in the way we want it to.
Exactly. Nanocatalysts are really important for making MTO catalysts that are more selective, more stable, meaning they don't deactivate as quickly and that last longer. And the main type of materials that we use for this are zeolites.
Zeolites, they pop up everywhere in catalysis. For our listeners who are into chemistry and material science, can you explain what makes zeolites so special for this reaction?
Okay, so zeolites are these crystalline materials made of aluminum, silicon, and oxygen, and they have this really well-defined three-dimensional network of pores. And inside those pores, they have these special sites called Brunstad and Lewis acid sites. So you could think of them as having these super intricate nanoscale structures with these acidic spots strategically placed within them. And the cool thing is we can control the size and shape of those pores and how strong and how many of those acid sites there are by changing how we make them and how we modify them afterwards. And this ability to fine-tune them lets us influence which reactants get absorbed onto the catalyst, which transition states get stabilized, and ultimately which reaction pathways are favored, so we get more of the olefin products that we want.
So it's like we're creating this molecularly engineered environment that's perfect for making ethylene and propylene and not so good for making those unwanted byproducts. So what are some of the best zeolite structures that have worked well for MTO?
There are a few different zeolite structures that have shown a lot of promise. One of the most studied and most important ones industrially is SaPO34, which stands for silico-aluminophosphate zeolite. It has small pores, which create this really tight space that forces the formation of mostly light olefins like ethylene and propylene, and it does a really good job of preventing those larger aromatic molecules and coke precursors from forming, which is really important for keeping the catalyst working for a long time.
And you mentioned another one earlier, ZSM5.
Right. ZSM5, which stands for zeolite Socony Mobile 5, is another really popular catalyst for MTO. Its pores are medium-sized, which often means you get a higher ratio of propylene to ethylene compared to SaPO34. And because the pores are bigger, it can handle those heavier hydrocarbon intermediates a little better, which can be useful depending on the reaction conditions and what kind of product distribution you're aiming for.
Are there any other zeolites that people are looking at for MTO?
Oh yeah, definitely researchers are constantly looking at all sorts of zeolite frameworks and trying to modify them to make them better for MTO. Some examples are beta-mortonite and SSZ13. Each one has its own unique pore structure and acidity characteristics that we can take advantage of to tweak the selectivity of the reaction or to improve how it performs under specific conditions. For example, some researchers are working on modified zeolites that are really good at making propylene directly because there's a big demand for that.
You talked about pore size and shape selectivity before.
Yeah.
For our audience, can you explain a little more about how those nanoscale features actually control what products we get?
This is where the creativity of catalyst design really comes into play. The size of the zeolite pores acts like a molecular sieve. In small pore zeolites like SaPO34, only small molecules like ethylene and propylene can fit through those channels and cavities. Bigger molecules like those polycyclic aromatics get stuck, and they can't form as easily, and they don't block up the active sites inside the pores. It's kind of like trying to fit different size needles through different size needle holes. Only the right size molecule can get through.
That's a great way to put it. So what about medium pore zeolites like ZSM5? How do they affect the selectivity?
Well, medium pore zeolites give the molecules a bit more wiggle room, which means they can make slightly bigger molecules like propylene. And the way those pores are arranged and where those acid sites are located inside ZSM5 can also affect how the reacting molecules are oriented and what the transition states look like during those key steps where carbon-carbon bonds are formed and broken. And all of that influences what the final mix of products is going to be.
And then there are these hierarchical zeolites, which seem to be really useful for preventing the catalyst from deactivating. Can you explain how having different sizes of pores helps with that?
Right, so traditional zeolites mostly have micropores, which are super important for their catalytic activity. But sometimes the molecules have a hard time getting in and out of those tiny pores. Hierarchical zeolites have a second level of porosity on top of those micropores, and these bigger pores are called mesopores. They're like super highways that let the reactants get to those active micropores quickly, and the products can get out quickly too. And the best part is that those mesopores give those larger Coke precursors somewhere to go before they can build up and block the micropores. So hierarchical zeolites are much better at preventing Coke formation, which means the catalyst lasts much longer, and that's a really big deal in industrial processes because it saves a lot of money.
So it's like adding a bunch of express lanes to that network of tiny roads inside the catalyst. What other tricks are researchers using to optimize MTO catalysts?
There's a ton of research going on in this area. One important strategy is to add tiny amounts of metals like zinc, gallium, or iron, either into the zeolite structure itself or just on the surface. And these metal modifiers can work together with the acid sites in the zeolite to further tweak its activity and selectivity. For instance, certain metals can promote specific reaction pathways that can change the ratio of ethylene to propylene, or they can help to suppress the formation of those unwanted byproducts.
That's really cool. And you mentioned something called core shell catalyst architectures before.
Yeah, core shell catalysts are another way to control how the catalyst behaves. In MTO, this might involve having a core material that's really active for MTO and then surrounding it with a shell that has different properties, like being resistant to coke deposition or being more stable at high temperatures. And by carefully engineering the boundary between the core and the shell, we can control the performance of the catalyst and prevent those deactivation mechanisms from happening.
And what about single atom catalysis? That seems like the cutting edge of catalyst technology.
Right.
How is that being used for MTO?
Single atom catalysts are like a whole new way of thinking about catalyst design. Instead of using nanoparticles of a metal, we take individual metal atoms and disperse them very precisely on a support material, which could be a zeolite or some other porous oxide. And in MTO, researchers are trying to use single atom catalysts to control specific steps in that complicated reaction network. And because the active sites are spread out so much, it can make the catalyst super efficient and potentially reduce the formation of those undesirable byproducts that you might get with larger metal clusters. It's a really exciting area of research that could give us even more control over the selectivity and stability of MTO.
It's amazing to think that we can manipulate materials at the atomic and nanoscale level and have such a big impact on a complex industrial chemical reaction like this.
Mhm.
So where are we seeing all these advances being put into practice in the real world?
Well, MTO technology is already being used in a lot of industrial settings. One of the best examples is Sinopec's DMTO process, which is located in Dalian, China. It's a commercially proven technology that can produce a lot of ethylene and propylene very selectively.
And what about the other big players in this field?
UOP and Norsk Hydro have also successfully commercialized their own MTO process, which uses SAPO34 zeolite catalysts. And ExxonMobil has been looking at combining an MTO pathway with their existing methanol to gasoline, or MTG technologies, which just shows how flexible this technology is and how it can be integrated with existing infrastructure in the petrochemical industry.
So MTO isn't just some theoretical idea. It's actually being used in industry right now.
Sure.
What are some of the challenges that are still out there, and what are the main directions that research is taking in this area?
Well, catalyst stability is still a really important focus. Even though we've made a lot of progress with things like hierarchical zeolites and other strategies, we still need to find ways to reduce coke formation even more and make those catalysts last even longer. And that's going to be crucial for making MTO processes more economically viable and more sustainable. And of course, we're always trying to optimize the process itself to get even higher selectivity for the olefins we want, while also reducing energy consumption.
Yeah, energy efficiency is always a big concern in industrial catalysis.
Absolutely. And then there's the challenge of scalability and cost effectiveness. We already have large-scale commercial plants, but it's important to develop catalyst solutions that are even more robust and affordable so this technology can be implemented even more widely. But I think the most exciting direction for the future, especially with all the emphasis on sustainability, is to combine MTO technology with the production of renewable methanol. If we can find ways to make methanol from sustainable sources like biomass-captured carbon dioxide or green hydrogen, then the MPO process could become a truly green way to produce those essential olefins. And that's something that I know a lot of you are interested in.
That's a really exciting vision for the future of this technology. So for our listeners who are studying or working in chemistry and material science, what are the key takeaways from our deep dive into the MTO reaction?
Well, I think the main points are that the MTO reaction is a really important and increasingly popular alternative to the traditional ways of making olefins. It gives us more options for where we get our raw materials from, and it opens up the possibility of using carbon sources that don't come from fossil fuels. And nanocatalysis is playing a huge role in making this process work better, especially the development of zeolite catalysts with tailored pore structures and acidity. And then there are all these innovative approaches like metal modification and single atom catalysis that are helping push the boundaries even further. And finally, integrating MTO technology with the production of renewable methanol has the potential to make a huge contribution to a more sustainable chemical industry.
It sounds like a game-changing technology, and it's really inspiring to see how fundamental research at the nanoscale is leading to innovations that have such a big impact on industry and society.
Definitely. And with all the research that's happening right now in areas like renewable methanol production, new catalyst materials, and reactor design, there's so much potential for breakthroughs in the future. So, for all of you listening, I want to leave you with a question based on your expertise and what you've learned today. What future breakthroughs do you think will have the biggest impact on making the methanol to olefins process even more widely used and more sustainable in the long term? It's a fascinating field with so much room for innovation.